Alright, so in this lesson we're going to start looking at the magnetic force on charged particles and how the magnetic field will apply a force on a moving charged particle. So if you have a charged particle that's moving through a magnetic field, it applies a force on that charged particle, and the magnitude of that force is given by Q times V times B times the sine of the angle between V and B. So this is really a cross product, Q times V cross B. And so all the magnitudes of those three values matter, but the direction also matters. If you had a V that was in the same direction as B, you would get zero force, or a V that was in the opposite direction of B, you get zero force. Where force gets maximized is where V and B are perpendicular to one another. So let's look at how we can actually figure out the direction of this force. We use, or kind of look at this. Here we have a charged particle moving parallel or anti-parallel to the magnetic field, so in the same direction or the opposite direction. It experiences no force. Here we have a particle that's moving across the magnetic field, not perpendicular. So here we have a force which would be perpendicular to the magnetic field and the velocity. And here we have velocity perpendicular to the magnetic field, and in this case the force would be perpendicular and be the largest. The magnitude of that force would be Q times V times B in this case. Now it's worth pointing out that we've done cross product before when we talked about torque, and so we know a way to figure out the directions of the magnetic force if we know the directions of the magnetic field and velocity. And so the way to do this is the right-hand rule. And so this determines the charge or the force on a positively charged particle that's moving. And so we put our fingers in the direction of B, our palm points in the direction of B, and our thumb would point in the direction of F. So if we look at these pictures here, if I look at the one on the far left, and I put my fingers in the direction of V, so kind of out toward me, B in the direction of the magnetic field to the right, my thumb does indeed point up. Now, for negatively charged particles, the force is in the opposite direction. There's a negative sign that gets introduced. And so there's one of two ways that you could do that. You could use the right-hand rule and just know that the force is going to be the opposite direction that you just predicted. Or you could use your left hand, because on your left hand, your thumb points the opposite way if the fingers and palm are in the same orientation. So sometimes I've heard the left-hand rule for negative charges, and that's another way to do that. So let's do some practice. We have a magnetic field into the page. We usually use these X's. I use X's to signify magnetic field into the page, which means it's going straight down into your screen. If you ever see me do little circles or little dots, that usually means magnetic field out of the page, coming out at you. What I think of is, I think of the arrow. The X is like the tail of an arrow, or the fletchings of an arrow, the feathers at the end. The point is like the point of the arrow coming out at you. So let's do some quick practice. Here we have a charged particle moving across this this magnetic field, and I want to know what direction is the force. So take a second and do that for yourself. So we probably would have guessed that the force is, well, I would guess upward on the page at this point. If we had a negatively charged particle doing the same thing, well, the force would be in the opposite direction, downward. What about a positively charged particle moving this way? Well, I get a force that's downward. What about a negatively charged particle moving up? If I do my right-hand rule, I get a force that's moving to the right. Now, it's worth pointing out that the force acting from the magnetic field is always perpendicular to your direction of motion. What that means is that this force acts a lot like another force we've seen, and that's centripetal force. If one of these charged particles, if we allowed it to continue to move, it's going to actually move in a circle. So force and motion are always perpendicular to one another. We can actually find the radius of that circle made by taking Q times V times B and set it equal to mv squared times r. If we solve that for r, we get m times v divided by Q times B on the bottom. So this would give us the radius of a circle that our particle is going to be taking. So let's do a quick example problem. We're going to have a proton that's moving at 1.5 times 10 to the 7th meters per second. It's going to enter a magnetic field that's directed into the page. with a uniform intensity of 0.5 Tesla. And I want to know, what is the radius of the proton's motion? First of all, we can figure out what is going to happen to the proton after it hits the magnetic field. It's going to curve in the upward direction. If you actually follow along with your right-hand rule, you'd notice that, yep, this does work. And so we can plug in some values. We know that's going to be r. I know v and t from the problem. I looked up the mass of a proton and the charge of a proton, and I find this thing would have a radius of 0.31 meters. So another device that we come across quite frequently when we start to look at magnetic fields is a device called a velocity selector. And what a velocity selector really does is it allows us to select charged particles with a specific velocity. It uses both the magnetic and the electric field and the forces on a charged particle from both the magnetic and electric field to choose the velocity of the particle. I say choose because what would happen to particles that are moving too fast or too slow is they can't get through the velocity selector. So if we have, say, let's say this is a positively charged particle, it's going to feel an electric force going downward due to the electric field. If it feels a magnetic force moving upward that's equal in strength, then this particle can move straight through this without being deflected. So remember that speed depends upon v. If v is too small, what happens is the electric force is too strong, and your charged particle ends up down over here. V is too big, the magnetic force is too strong, and you end up over here. So there's a very specific v that allows you to get through this arrangement, and if we actually do the math, it's related to just the electric field strength and the magnetic field strength. Now this is another weird one that I challenge you to go back and do the unit or the dimensional analysis for. If you do the dimensional analysis of newtons per coulomb divided by Tesla, you do actually get meters per second to pop out of it, which is completely crazy to me, but dimensionally this works out. So in a velocity selector, you can change what this velocity is by changing either the electric field strength or the magnetic field strength is. Where velocity selectors get used, they used to be used in pretty much every TV that existed, because if you had a cathode ray tube TV or a cathode ray tube screen, there's a velocity selector at the end of it. I'll probably show you one like that in class. They also get used quite frequently when you're dealing with things like X-rays or radiation treatment, things like that. You want specific velocities of particles. So here you have an arrangement where you can actually select the velocities of the particles. Another device that uses this is what's called a mass spectrometer. And so in a mass spectrometer, we use a velocity selector and a magnetic field to separate particles of different masses. So what the velocity selector does is it selects the particles with just a speed v. Now it's worth pointing out in my velocity equation, the mass and the charge of the particle doesn't matter. So what a mass spectrometer really is doing is it's separating particles based upon mass. So they pass through this velocity selector. Only particles with speed v can get through it, and they enter this uniform magnetic field out here. So basically we have a magnetic field in this whole region, and so the particles will undergo kind of that centripetal force motion. Now if we look at mv squared over r, more massive particles would travel in greater radius. So we can actually then collect particles based upon mass over on this detector. What this device really does is it'll help us determine the amount and types of substances present in a sample. Usually how we do this is we singly ionize everything, so we know that we know their charges are all the same, and that way this radius is going to be solely dependent on mass. So here we have chloride ions that are all singly charged, so Cl minus, entering the mass spectrometer at a velocity of 3 times 10 to the 5th meters per second, and the magnetic field is 0.5 teslas. What I want to know is what distance S3 would I need to place the collector to collect ions from each of the major isotopes of chlorine. And we have chlorine 35 and chlorine 37, the two major isotopes, and I've given you the mass of each of those. So it's worth pointing out that it wants to know the distance from S3, so from here. How far would I need to put the particles in there? So this distance is going to be equal to twice the radius. I know the radius is mv over qb, if I do mv squared over r times qvb and actually work it out. And so the distance would be twice that value. So if I plug in all the information for chloride 35 and chloride 37, we can get our two values. That the chlorine 35 is going to be hitting that detector at someplace 43.5 centimeters away from S3, and the chlorine 37 would be at 46 centimeters. So how this device works is you have this long particle detector. It has individual little sensors at various distances, and when a particle hits it, it counts that particle. And so what you'd see in a mass spectrometer is you'd see really two spikes of particles, one at about 43.5 centimeters and one about 46 centimeters. So that's how we deal with individually moving charged particles. What we'll do in the next lesson is we'll start looking at what happens if we have a current carrying wire.